A streak of ice and rock traveling faster than anything we've ever seen drifts through the solar system. For months, astronomers have followed its path, watching it silently cut across the void. It is not a comet from our sun, nor a wandering asteroid from the outskirts of our system. It is something else entirely. 3I Atlas, the third interstellar visitor ever recorded, a ghost from another star, arriving unannounced, leaving mysteries in its wake. We can't see it anymore. Our telescopes lose it in the glare of the sun, but the data we've gathered tells a story of speed, size, and composition unlike any object we've ever encountered. In just a few months, this comet has challenged everything we thought we knew about objects traveling between the stars, and it is only beginning its journey. Where did it come from? How did it survive the billions of years drifting through the dark? And what secrets does it carry from its distant home? Today, we start tracing the path of 3I Atlas, uncovering the astonishing story of a visitor that arrived from the heart of our galaxy. As 3I Atlas speeds toward the Sun, it enters a phase astronomers call Perihelion, the closest point in its journey to our star. On October 29th, it will pass roughly 210 million kilometers away, just inside Mars's orbit. That distance may seem vast, but in the grand scale of the solar system, it's close enough to heat its surface, releasing material in a spectacular display. This is where the comet truly begins its cosmic dance. Heat from the sun causes sublimation, a process where solid ice transforms directly into gas. On Atlas, this produces a glowing coma, a fuzzy halo of dust and gas, and eventually a long tail that streams away from the sun, pushed by the solar wind, a continuous flow of charged particles from our star. But Atlas isn't a typical comet. Unlike most, which start forming comas around 3-4 AU from the Sun, Atlas began forming one beyond Jupiter's orbit, over 5 AU away. The secret? Carbon dioxide ice. Sublimating at much lower temperatures than water ice, it created a halo long before the Sun's warmth could affect it. As Atlas approaches, water vapor joins the mix, forming one of the most unusual and dynamic comas ever observed. Even more fascinating, early images show its tail initially pointing toward the Sun, defying expectations. Only later, as the solar wind strengthens, does the tail realign away from the Sun. This unusual behavior tells astronomers that Atlas's interactions with the Sun are already revealing secrets about its composition. Secrets that hint at a life far older and stranger than anything in our own solar system. When 3I Atlas was first spotted in July 2025 by the Asteroid Terrestrial Impact Last Alert System, astronomers thought it was just another asteroid. But soon, something extraordinary became clear. It was moving far too fast. Objects in the solar system orbit the Sun because of gravity, and the closer you are, the faster you must travel to avoid falling in. Earth moves at 30 kilometers per second, Mercury at 48 kilometers per second. Atlas? A staggering 58 kilometers per second, even while still near Jupiter's orbit. At that speed, it wasn't bound by the Sun's gravity. Atlas was on a hyperbolic trajectory, meaning it came from interstellar space and would leave again, never to return. It was the fastest object ever tracked in our solar system. Its velocity and path immediately distinguished it from the usual asteroid or comet. This was how 3I Atlas earned its name, the third interstellar visitor observed after Oumuamua and Borisov. Unlike its siblings, Atlas was bigger, potentially 5.6 kilometers wide, and faster, moving almost twice as quickly. But the strangest part was its direction. While Oumuamua and Borisov came roughly head-on, following the Sun's motion through the galaxy, Atlas entered almost perfectly aligned with the plane of the solar system, a rare T-bone encounter only 3 degrees off from the ecliptic. This precise alignment is more than a coincidence. It suggests that Atlas didn't just wander randomly through space. Its journey was shaped by cosmic forces that funneled it into a near-perfect path through the solar system, giving astronomers a rare, front-row view of an interstellar object interacting with our planets. So where did 3I Atlas come from? To answer that, astronomers had to look far beyond the solar system. Its hyperbolic trajectory pointed straight toward the galactic core, the densely packed center of the Milky Way. From above, the galaxy looks like a swirling spiral, with stars tightly clustered near the center and more sparsely scattered along the spiral arms, where our solar system resides. Atlas came from this bright, ancient heart of the galaxy. But space is three-dimensional. Just like our solar system has a thin disk of planets and asteroids called the ecliptic plane, the Milky Way has a thin disk of stars. Most of the chaos, the collisions, supernovae, and black holes happens there. Above and below this disk is the thick disk, a quieter region where objects can drift undisturbed for billions of years. This is likely where Atlas originated, making it possibly over 7 billion years old, nearly twice the age of Earth. Even though 3I Atlas was officially discovered on July 1, 2025, its first traces appeared earlier on May 7th, captured by the Transiting Exoplanet Survey Satellite, TESS. TESS wasn't looking for comets. It searches for planets around distant stars, but by sheer luck, its gaze intersected Atlas's path. For about a month, TESS tracked the object as it moved from beyond Jupiter's orbit toward the Sun, giving astronomers a rare early glimpse of its behavior. The first clue about its true nature came from brightness measurements. As comets approach the Sun, the heat causes sublimation, releasing gas and dust that reflect sunlight, forming a coma. Over that month, astronomers expected Atlas's brightness, or flux, to increase modestly, about 1.5 times. Instead, it surged fivefold, signaling the early formation of a gaseous envelope, which only develop comas between 3 and 4 astronomical units. But brightness wasn't the only surprise. The polarization of light from Atlas's coma, how sunlight scattered through the gas, was extremely unusual. While most objects show positive polarization, Atlas exhibited strong negative polarization, the most extreme ever recorded for a comet or interstellar object. This suggested its surface and coma particles were fundamentally different from anything in our solar system. Rather than being dominated by water ice like most comets, Atlas's early coma was rich in CO2, with a ratio of roughly 8.1 compared to water vapor. CO2 sublimates at much lower temperatures than water ice, explaining why the coma formed at such a great distance from the Sun, beyond Jupiter. The sublimating CO2 may also have dragged along nickel atoms, another strange feature, while iron remained undetectable, raising questions about the object's formation and history. This early observation period revealed something profound. 3I Atlas was not just another comet. It was a comet from another star system with entirely unfamiliar chemistry, carrying the secrets of its long interstellar journey. As 3I Atlas continued its journey inward, approaching the orbit of Mars, astronomers observed dramatic changes in its behavior. By late September 2025, the comet had begun releasing vast amounts of water vapor, equivalent to a fire hose running at full blast. This sudden outpouring was far beyond what is normally expected from a comet at 1.5 AU. Metals in the coma also started to appear. Early in the summer, telescopes detected nickel, but no iron, which is unusual because both metals are typically formed together inside stars and are usually found together in comets. The lack of iron raised questions about what processes might have separated these elements over Atlas's long interstellar journey. However, by late September, iron began to appear, and the ratio of nickel to iron gradually normalized. This suggested that Atlas was slowly settling into behavior more typical of comets in our solar system, though in a highly unusual sequence. Then came the formation of its tail. Most comets have tails that point away from the sun, driven by the solar wind pushing gas and dust from the coma. But Atlas initially formed a sun-facing tail pointing toward the sun, likely due to the early sublimation of CO2 at large distances where the solar wind was still too weak to shape it. By September, however, a short fan-shaped tail facing away from the sun appeared, more in line with what we expect from a typical comet. These transformations highlighted just how extraordinary 3I Atlas was. It was a comet behaving like no other, from its early CO2-driven coma to its metal anomalies and unconventional tail development. Astronomers realized that observing these changes could offer rare insights into the chemical and physical properties of interstellar material, potentially revealing secrets about other star systems far beyond our own. By early October 2025, 3I Atlas made its closest approach to Mars, passing just 0.19 AU from the planet. This fortuitous alignment gave astronomers a rare opportunity. Unlike Earth, Mars had several cameras in orbit and on its surface capable of capturing images of the interstellar visitor. The Perseverance Rover snapped a series of long-exposure photographs. Each exposure lasted 30 seconds, and several images were stacked to enhance the faint signal of the comet. The result was a streak of light across the Martian sky, giving scientists a first-hand look at Atlas's coma and tail from a new perspective. Meanwhile, the ExoMars probe orbiting Mars captured sharper images, though still lacking the resolution to distinguish between the surface and the bright coma. These observations provided invaluable data on how the comet reacted to solar heating at close range, filling in gaps that Earth-based telescopes could not. As 3I Atlas continued its outbound trajectory, the sun temporarily blocked our view, leaving astronomers in suspense until early December 2025, when it would emerge on the far side of the sun. At that point, observations would focus on how perihelion had altered its structure and activity, especially after such a dramatic encounter with our star. The comet's final close encounter within our solar system would occur on March 16, 2026, as it passed 0.36 AU from Jupiter. Its journey through the solar system, though fleeting, offered a once-in-a-lifetime chance to study material formed in distant star systems, perhaps shedding light on the processes shaping planets, stars, and comets far beyond our own celestial neighborhood.